Recording. Okay.
So
this is, yeah, go ahead.
The time changed because it says on one of the slides that the final was on Monday instead.
It's on Wednesday. That is correct.
Okay, so it's on Wednesday.
Yeah, I got to follow the NAU final exam schedule, and I can't ask you to take a final at any other time. So the Zoom finals, the remote finals, and the in-person finals will be at the same time. And there'll be few enough people in here, this is a small class, that I'll be able to manage it. So Zoom final at the same time in Zoom as the in-person in EGR 234. Wednesday at 3 to 5 because my, whatchamacallit, my, it's definitely not Monday. Monday is my 280 exam. The last homework is due, well, you had a homework due today, and then the last homework is due on Thursday. It will be on ADCs and DACs. If you accidentally did the 280 homework that was originally posted to BB Learn, I'm sorry, you can send it to me, the completed 280 homework, and I'll give you some extra credit points somewhere. Please do the 380 homework that's posted now. There was a bunch of stuff on BJTs. Okay, I'm sorry about that. A couple people have gotten bonus points over it. Grade increasing opportunities, 5 points extra credit on the final exam for the course evaluation. The practice finals worth 10 points on the final exam. I just add them up and add it to whatever your score is. Homework 11, 25 bonus points. Homework 12, there's 5 bonus points. And I will take 1 week worth of late lab to my email by this Friday. And don't ask me after that because I got to get grades in. You have an 88% or greater overall in the class and you've turned in lab 4, there is a column in BB Learn called final grade. If you have an A in that column, it will remain an A, okay, even if you don't take the final exam. So you don't have to take the final exam. I had one person actually come in and wanted to take the final exam until they saw it, and then they didn't. They decided they didn't want to after all. So best thing to do is study. Generally, it's just not that bad. Sign up for 490 in the fall. It's open. We're up to 7 people now. Both Michael Garcia and Michael Not Garcia will be in there. Yes. You'll get to meet the famous Michael Not Garcia. And also, if you want to take a semiconductor physics class, Daphne Chen is teaching a class on that. My 490 in the fall is kind of like suitable for both circuits people and power people, in that we're talking more about PCB design. Yes.
How much harder is 599 in comparison to 490?
My 490, they're like light years apart. My 490 in the fall is fairly easy. If you can just, it's basically we're testing circuits and we're writing test reports on them. And I don't grade them too roughly. It's more like I just want you to learn the skill. And I don't tell you exactly what I want because I want you to learn to work with vagueness. And since I don't tell you exactly what I want, I accept a lot. For $5.99, what she's using is the textbook that I used as a first-year graduate student, Simon C. That's SZE. Device physics class, and it's tough. If you really like physics and you're into it, it's great. Best person to talk to about it would be Max is in that class. Jordan, you're in there too, aren't you?
Neither Max or I took it this semester.
Oh, okay. You're just working for her.
Yeah.
Okay.
So,
which Sean? Robbins, yes. So talk to Sean Robbins. He can give you some advice on what they're doing in the class.
He said it was difficult, but it's kind of an interesting setup We
Mhm.
have one exam and then a final presentation
Okay.
instead of.
Okay, so Jordan's saying there's only one exam and then a final project, but expect to work harder because it is a graduate level class.
Okay.
Data converters. Okay. Where are we at? We're at the analog ramp generator. This is where we left off. So basically, I've got this offset voltage in here. We're including that, and we put it in there as a negative voltage. So this is when we do the transfer curve of this, if we do it in the time domain, and this is done in a lot of textbooks, what you get is the V out over Vn is going to be related to 1 over RC times the integral from 0 to t of whatever VR of t is. So when I plot that, if VR is a constant value, oh wait, I'm going to start out at negative VOS. And if VR is a constant, when I integrate that, I'm going to get something that increases linearly with time that has a slope of 1 over RC. So if I can take this and run it into if I can take this and put it as one input into a comparator, this is a constant voltage. This is my input voltage. This is a reference voltage. And compare it to my input signal and see if my input signal is a constant, Vn. Wow, that is a straight line. I'm proud of myself. I can see how long it takes for my ramp to get to my input voltage, and this amount of time will determine what my input voltage is. That works great if I know the very precise value of 1 over RC, so I know the slope of that line. Problem is, real resistors and real capacitors have variations. The resistors in the parts cabinet over here are 10% resistors. So this is plus or minus, R plus or minus 10%. The C, when you buy capacitors, they can be 20, 50%. So you don't really have a really good accurate thing of what your RC is unless you do things like you measure them precisely for every single device in production, or you do some kind of laser trimming to get the gain where you want it to be. That can be done. You can't do that in 286. Sorry, Dr. Sherber. It's not Dr. Sherber. Sorry, Sherber. So that's the idea behind this. And what I'm going to do, so I have this analog ramp generator right here, built with that simple integrator. I want to be able to reset it. Now, this is not in any of the textbooks here. When you look at Cedric Smith and you look at any textbook, they leave this reset out. Like this thing just integrates all the time. The problem is if you integrate all the time, you get these little offset voltages in here. You're integrating the offset voltage. This thing saturates. It goes to plus or minus whatever my power supply is. I have to be able to discharge this capacitor occasionally. And I want to discharge it at the start. So I just close that switch to discharge it to ensure that there's no charge in that capacitor at the beginning. We'll build the circuit and watch you guys in 490 in the fall, and I can like watch you guys struggle with this. Big thing is you need a reset switch on it. A MOSFET or capacitor works, or MOSFET or a BJT works. So I want to build this thing. I've got a reset on it now. An analog ramp generator. I start the conversion. I let the reset go. I'm running this in. My start starts an in-bit counter. And what I'm doing here is I take the analog ref generator and I compare it to ground. So when this goes high, I can actually clock this circuit at whatever clock speed it's going at. It enables the clock. This goes into a comparator here. I'm comparing the ramp to my input signal Vx, and I'm waiting for this to go from low to high. When it goes from low to high, I trigger this flip-flop, which gives me an end of conversion signal, which goes back in and stops the clock and stops the counter. And somebody's calling me. I don't know who that is. Okay, stops the counter and saves this count value as the output. So basically what's going on here is I'm going up, I've got a ramp generator, so it goes up 1 tick, whatever that is, every clock cycle. It goes up, it goes up, it goes up, it goes up. When I get to this point right here where they cross, my end of conversion signal goes off. So right about here, my end of conversion signal goes off, and that will be what I store into my, whatever numbers on the counter then becomes what I store into the output. I need to know RC, that's a problem. So I need a better thing here. And in order to get the better thing, you need a negative power supply. I'm sorry, it's like bane of people's existence for some reason. What I'm going to do here is I am going to take this thing. It has a variable slope. The slope of this for my ramp generator going up is going to be the input voltage divided by RC. So if I get a bigger input voltage, it's going to go up to a higher voltage in a fixed amount of time. My phase one, I fix the amount of time I allow this to integrate. And I'm looking, I've got this voltage level right here. We don't have it turned into a digital number yet. Then I take a negative slope generator and I subtract off something that has a slope of Vref over RC. So this has a fixed slope. They're all going down at the same rate, regardless of what the input is, because that slope is determined by Vref. And I figure out how much time does it take to go from this peak value down to 0. That's going to be what determines my output. So I count up while I'm integrating Vx. I count down while I'm integrating Vref. And the RCs cancel out because the slopes of the two are dependent upon the same RC. This is how you get accuracy even with cheap parts where the capacitors can vary by as much as 50%. You think you get a 1 microfarad capacitor when you pull it out of the cabinet. That's 1 microfarad plus or minus 20 to 50%. There's huge variations in caps because it's harder to control them. So yeah, that's where we get there. Okay, so how does this work? Here's a dual ramp generator. I have to be able to switch. So these are just MOSFETs again, or some other transistor. I need to switch whether the input's going to Vx or whether it's going to Vref. So I start out by integrating Vx. It's a negative value, and this is an inverting configuration, so I'm expecting to get a positive voltage out. If I have, okay, 16T, here's my time. Oh, good, it's drawn on the next slide, so I don't have to do this. As I integrate up on Vx, I'm going to get this going up, and then I store that voltage is stored right here because it's stored across the capacitor. Then I switch VX off, and I go into cycle 2 and I tie VREF in, and then it's going to go, because VREF is positive, the slope's going to go in the other direction, and I integrate this down and I see how long it takes to get to 0, because I'm comparing it to 0, and that's going to determine how many counts that takes to get there will determine what data I get on the output. So I don't want to talk about that, Dr. Brown. I put in VX3. It's going to take 8 clock cycles for this ramp, roughly 8 clock cycles, for this ramp to integrate up to VX3. I take in a lower value, VX2. It's going to, in that same fixed amount of time, 8 clock cycles, it's going to integrate to a lower value. And I take an even third lower voltage, VX1. It's going to take 8 clock cycles to integrate up there. Because remember, the slope is VX over RC. Doesn't matter that RC is, we don't precisely know the value, as long as it's not too big, or not too small in this case. As long as it's not too small, we can just figure out what voltage it goes up to. I put a higher voltage, it's going to integrate up to the higher voltage in time. Then I go through and I see, okay, how many clock cycles does it take to integrate down? And that slope is proportional to VREF, which is a fixed voltage, over RC. And through the magic of transfer functions, when I flip them over and the RCs cancel out, I'm going to get, this took a little more than a clock cycle. So I'm going to count that up and call this, okay, so where's my start point? My start point's right here. I'm going to call this, it was a little more than 1, so I'm going to say, assign this a digital value of 1. When I get right here, it takes 1, 2, 3, 4, a little more than 4 clock cycles to get there. So I'm going to give this a digital value of 4, 1, 0, 0. This one here took, how many? 1, 2, 3, 4, 5, 6, 7, a little more than 7. So I'm going to call this digital 111.
By changing your viewer, different precisions.
Yeah, you usually don't change VREF, but you could get, if you change VREF, what you're changing is the full scale range of your converter. So, I mean, you could play around with that. Let's say I have a signal that is going, oh, we'll do this in multiples of 8. I have I put VREF at 16 volts. Then each bit is going to count, on a 3-bit converter, is going to count for 2 volts. I get a lower precision on that. If I knock VREF down to 8 volts, now I've got a 1 volt range. But if my signal's going 0 to 15 volts, that's probably a bad idea. Okay. Always go with more bits. What was the one? Oh yeah, Bilal. I miss him. Bilal built this we went out and bought this 24-bit converter for the lab, and we got it all working because we were grousing about the precision on the. At the time, we were using Arduinos. It was way back in the dark ages. We were using Arduinos, so we didn't like the precision on the converter there, so we just bought our own and put it on there. Since then, we've moved up to Wi-Fi, which is a little bit better. It's still Atmel, microchip, whatever you want to call them, but it has more functionality. Now we're hitting the wall of functionality of the Wi-Fi boards, so we're building FPGAs, is the idea. Okay. So good, I went through and did this. We've got different kinds of converters here. We've talked about, the first one we talked about was the counting converter. This is where we do a linear search. We just count up. We have an n-bit counter. We count from 0 to 2 to the n, or 2 to the n minus 1. And we feed that into a DAC, and we use that for what we're comparing our input to. When this changes state, we know we've reached the end of conversion and we're done. I have to possibly go through 2 to the n states. So it takes 2 to the n clock cycles to go through it. That's a linear search. The single ramp is also a linear search, not quite as accurate. And we just went through that. And the dual slope gives us more accuracy, but it takes about twice as much time to get there. We talked about the binary search, where I go through and I guess the first bit and decide if it's too high or too low, and then I can do the next most significant bit much faster. These generally take 2 to the n clock cycles to finish, and this it takes 2 to the n times 2 clock cycles to finish. This takes n clock cycles to finish. Flash is the one we're going to talk about next. It takes 1 clock cycle to finish. Much faster, much more power hungry, and takes up more area. These I can do with some simple control logic, a couple of counters, a couple of comparators, nothing too big. This I need 2 to the n comparators and 2 to the n resistors. And this is my next education term for the class, scaffolding. And basically what this is doing is kind of what we've been doing since 188 and what you've been doing since kindergarten, is you take simple concepts and you build on them. Like you learn that's a bad example. You learn digital logic. You learn those logic gates, and then you start putting them together in bigger systems and finally building computers. Okay, this is a parallel search. This is a flash converter, and this is why flash converters are so fast and so power hungry. I put in VREF of 1.6 volts, and I'm comparing it to VX of 0.35. Oh, great. Let's do this. Get out the stupid calculator. Yeah, I agree. Sorry, I just saw my text messages. 1.6 divided by 0.35 gives me 4.57. So this is putting somewhere between, let's see, 1, 2, 3, 4, 5. Wait, is that right? This is 1. Okay, so this one's going to trip off when I get to a half. This one's at 1.5, 2.5, 3.5. I just had a conversation. 4.5. So, and this is 5.5. My VX is going to end up right about there, where this one will be converting. Okay, so what I've got here, when I'm writing the numbers I'm writing down, refer to the LSBs. Note here that this one's at R over 2. So I get a half an LSB before this one trips. So this one's I will get this value out between 1/2 and 1.5 LSBs. If I put in a number that's up here, what I'm going to get is 0, 0, 0, 0, 0, 1, 1. All those conversions take place at the same time. If all I'm doing is comparing VX, which in this case is oh, that's not right. How did I get that? 1.6. I'm sorry. It would be 0.2 volts. Let's put this in terms of voltage. Oh, I did that thing again. This is in terms of voltage. Let's just change colors here. That was in bits. This is in terms of voltage. So 0.2 volts. This actually wouldn't be 0.2, it'd be 0.1. It'd be half an LSB. This one would flip at 0.3, and this one would flip at 0.5. So actually it's somewhere in here. So this would be 0. This one would go at 1. And I would store the number that corresponds to the lowest value comparator that flipped. Did that make any sense? Some people are nodding. Okay. Yeah, I just explained that. So what I need here for every bit, I got 1, 2, 3, 4, 5, 6, 7, 8. 8 resistors. I need 2 to the n resistors. And I need 2 to the n comparators. So it's large, it's power hungry, but it's extremely fast because all of the comparisons happen at the same time. And my control logic just needs to look at which bit where this changes and convert that into a 3-bit number. Okay, flash converters, and then go back and look at this again. And I'm skipping this because I don't want to talk. It's a switch cap circuit. I'll talk about it philosophically. We have a whole bunch of other stuff to do. Motivation, it's the end of the semester and I don't have a whole lot of motivation. What? Okay, I know. I just want to get to this part because this is what's on the homework. The other part isn't on the homework so much. We're going to look at some basic nonlinearities and we'll talk about these more in 490 in the fall. Offset error, gain error, differential nonlinearity, integral nonlinearity, and these things which I can't tell the difference between based on the formulas because they come out the same to me, absolute accuracy and relative accuracy. Every DAC and every ADC that you buy is not perfect. Some those resistor values vary, the component values, the threshold voltages and the offsets on the components, on the comparators vary. They vary with temperature, they vary with time. But going out the door, the manufacturer wants to give you a good product, so they test everything and they test it against a specification. The only thing that you're guaranteed is that it will be as good as the worst case on the specification. Things that are not on the data sheet, that are not specified, you just assume that they're bad. Like the output resistance on the Arduino, whatchamacallit, ADC and DAC, it's horrible. You assume it's bad. You buffer everything.
You get 497.
What?
You get 497. Determine the output resistance.
Oh yeah, that would be a good one. We can do a project on that. I've got some of these. I've got like 3 or 4 different projects in that cabinet. I'm gonna have to look at my stash and see what I can do. Okay. So here's my perfect resistor string DAC. Every resistor is exactly R. And when I go through here, I'm going to turn on one of these transistors, and that's going to determine which place on this voltage divider goes through here. I have a perfect buffer that has a gain of 1 and no offset voltage sitting right here. The step size in LSBs, I put one more binary digit on here. I'm going to get 1 more volt on my 3-bit DAC with a full scale range of 8. That's perfect. Now what can happen in the real world is these resistors are not perfectly matched. You can laser trim some of these, but it's not, you know, you still don't get, you get maybe down to 1%. This right here that I assumed is 0 is really 0.001 R. There's some resistance to ground. This one's really 1.01. This one's 0.96. I get a variety of resistance values in here. So for this first step, instead of flipping at 0, it flips a little bit higher. I get an offset. The first one's a little too big. The next one's a little too small, and I'm exaggerating this. The next one's a little too small. And I go through here and I get I get a less than perfect thing here. The thing that most people want to know about is they want to know which one of these is the worst. Well, this one's off by 0.04, whatever R is, and this one's off by 0.04 of whatever R is. So this is going to determine how big of a step I've got there. This one's going to be a little bit small, and this one's going to be a little bit big. They want to know which one, they just want to know in general, how big is the biggest step size going to be? And this looks like it's about 4%. But we'll go through and we'll do the calculations in a minute. So yes, I put the numbers in today because this always drives me crazy. Oh, the way Dr. Brower words things. The gain error, generally I want 0, 0, 0 to be 0 LSBs, and I want 1, 1, 1 to be 7 LSBs. Exactly. Not 7.05, not 7.06, 7.00. So that can be quantified as gain error. Now this gain and offset error I can easily correct for. I can generate a quick algorithm to correct for them. And I've seen ADCs that are so bad and our computing power is large enough now, is what I did is I had the students run a gain curve. And I found, okay, if you you measure every single code and every single output voltage, and you store that in a lookup table. And if you get that code, that's your voltage. You know, that's another really easy way to correct if you have a lousy ADC or DAC, like in an Arduino. You've got a lookup table for 1024 states. I mean, you can store that in 4 or 5 kilobytes, or you know, for 10 bits, you can store it in 10K bits, and not a lot of memory. So those things you can correct for. Differential nonlinearity takes a little bit more computing power to do. You have to do the lookup table thing. For differential nonlinearity, I want each step size to be exactly 1 LSB, not 0.99 LSBs. What I spec is the worst case here. I go out and I measure it and I find the one that is the smallest or that is the biggest, the worst percentage offset. That's what gets written into the specification. So 99% of the all but one of them have a perfect differential nonlinearity. Their step size is exactly 1 LSB. One of them has only 0.5 LSBs. My differential net nonlinearity for that one has been shy of 0.5. Now, integral nonlinearity is a little bit harder to do. We'll look at this in a picture. We want the outputs to be on a 1-to-1 line. We want the slope on there to accumulate linearly. So if I have one that's a little bit small, followed by one that's a little bit big, they tend to cancel each other out. If I have a whole string, like my lower half of my converter is at a little bit small, and my upper half's all at a little bit big, I'm going to have a line that bows out like this, and I'm going to get a big integral nonlinearity, because that just means that at half full scale, I'm off by a lot. There's pictures that are better than me waving my hands. Coming up. Now the gain and the offset error, and we'll do a quick correction by hand here. What I do is I correct my 0 to be exactly 0 LSBs equals 0 volts. So it's going to be perfectly on that line. And I'm going to correct my 7 LSBs to be exactly 7 volts. It will be exactly on the point. So the ones that have been corrected, and it's hard to see on this for me, are this little heavier circle line. They're still off, but they're not off by as much, and they've done a gain and offset correction. So let's go through the math of doing this. I probably make more sense of it. So I get this data. I put in an input. I put in an input voltage of 0 volts, and how do I measure a 1/10 of an LSB? Okay, we'll get into that black med. Oh, maybe I won't. And I measure 0.1 LSB. Okay, so this is probably, I'm just not going to go there. I'm off by exactly 0.1. When I correct for offset error, I'm going to correct every single bit by that same amount. I'm going to assume that that stays constant. So this is 0.1. I'm going to subtract 0.1 from here to make this 0. I'm going to subtract 0.1 from every other bit. So this is corrected for an offset voltage. 4.05. You have to do this on the homework. 5.05, 6.2, 7.07. Now, when I do an offset, now doing a linear correction, you can do two things. You can subtract a fixed number and you can multiply by a fixed number. If I subtract here by 0.07, when I subtract here by 0.07, I'm going to mess up this value. So the only other thing I can do is multiply. So to get this to be exactly 7, I'm going to take this number and divide it by 7.07 and multiply it by 7. And that's my gain correction. And then I have to go through and do that for every single value in there too. Now, the step size is how many LSBs did I have to get to the next step? So here I'm going from 0 to 1.09. It was 1.09. From here, I'm subtracting off. I've got 1.98 minus 1.09 is 0.0889. Thank you. Okay, and I go through and I do that, and I get the step size. Let's just go through because I don't want to do all the subtractions, and I filled this one in. So I go through and I calculate the step size, and the step size is the previous minus the current. There's a little code down here. This was the old minus 0.1 because I wanted to make this 0. This is the old by mean the previous column, times 7 divided by 7.07 to make this be exactly 7. Now I'm taking the previous value minus the current one. This one didn't have a previous, so that's 1.09, that's 0.89. 2.77 minus 1.98 gives me 0.79. I find the differences in there. And for my specification here to get, oh, and at first I got to do DNL. So this is my step size. The DNL is the difference between this number and 1. I wanted to ideally go up 1 LSB for every step I put in. This has a difference of 0.09. This one's a little bit small, so it has a difference of negative 0.11. This is the difference, the step size minus 1. Okay, and I go through here, and now the DNL I'm going to report is I look for the number that has the largest absolute value. And that would be right here. So the DNL of this converter is 0.24. Now I want to figure out the integral linearity. This is a running sum of the DNLs. Because if I think about this, if this one's a little bit small, this one's a little bit big, this one's a little bit big, my integral nonlinearity is 0.09. Now for the next step, it was a little bit small. So when I add 0.09 with negative 0.11, I get pretty close to that line. I'm at negative 0.22. This one is negative, so it makes it smaller. This one is big, so it makes it bigger. And I just do a running sum on here. So this is 0.09, 0.09 plus minus 0.11. This number is this number minus 0.21. This is this number plus 0.24, and I'm doing a running sum going up there, kind of like integrating, why it's called integral nonlinearity. I find the number in this column that has the biggest magnitude, and that's right there. So my integral nonlinearity that I report is 0.23 of an LSB. Yes?
So long story short, is our differential nonlinearity is just the difference between our actual step size and the ideal step size.
Mhm.
And then the integral nonlinearity is the difference between the actual output versus the ideal.
Yeah, that one-to-one line. So it's how far it's deviate. The integral nonlinearity is how far it's deviating from the one-to-one line. The differential nonlinearity is how wide each bit is. Now I've seen, and this is the horrible converter that we started out with at JPL, but I've seen converters that have what they call missing codes. That's a DNL of 1, because there is at least one bit in there that has a step size of 0. So that's missing codes. And not only did it have missing codes, it had missing blocks of codes. So you could go, you might go from, on a 10-bit number, you might go from, you know, miss whole 5 whole segments. It might jump from like 0, and then the next code that you could possibly get out would be, I'm trying to say a 10-bit number in binary, a half full scale or something like that, or quarter full scale. It's missing all the codes in between there, and that's kind of what we were seeing. And it was this capacitor scaling problem, like I was talking about last time, is that the smallest bits were done just as being, he had a really long capacitor, and he just made it really short. And they had a different perimeter to area ratio. So when you got into the smaller bits, the scaling wasn't as good. But you could see, the funny thing is that you took a picture of this, you could see it. And George looked fine. And George was George Washington. It was our test pattern. It was dollar bill. Today we were looking at somebody who did a test pattern with a 20. I wonder how long that lasted in the lab. Lunchtime. Okay, let's go get Andrew. Okay. So this is accuracy, and this is what you're asked to calculate in the pre-lecture quiz. VREF is 1.6 volts. My N is 4. So my VLSB is going to be 1.6 divided by 2 to the 4th, which should be 0.1 volts. So this one's going to be harder. We want to calculate N. So in that case, I've got VREF is 1.6. Oh, okay, so this formula here, let's just write down what the formula is, and then I can solve it. This is VREF over 2 to the N equals VLSB. Now in the next part, we're given VLSB and we're given VREF. So we get VLSB, oh, is this the hard when the horrible part comes, over VREF equals 2 to the N. If we want to solve for N, we have to take the log to the base 2 of VLSB over VREF. Now my TI Inspire can do logs to the base 2. I just put, it's easy, I put it in. Most old calculators wouldn't do this, but there's this old stupid logarithm trick that nobody remembers until I remind them of this, and until I get to digital communications and I remind them of this, was the point when it would come up. If I want to find the log to the base 2 of N, and this works amazingly enough, I take the log to the base 10 of N, and I divide by the log of 2, log to the base 10 of 2. And it's a way of converting bases. If your calculator won't do that. Okay, where are we at? Almost done. I'm as tired as you. I'm probably not as tired as you guys are. It will be next semester. You can laugh at me then. I used to redo my notebooks every semester when I had a whole bunch of time, when they counted all my hours. It was real. The absolute accuracy, instead of using VLSB, we use the largest difference between the actual output and the ideal to calculate the effective number of bits. This is usually put on the data sheet for a lot of things. And this absolute accuracy, and I can never remember the formula, is going to come out to be the log to the base 2. So I'm doing that calculation of number of bits of 2 to the n over my worst case bit error. So for the converter that we just looked at, my worst case bit error happened right here. It was at 3 for my integral nonlinearity. And I was off by 0.23 bits. So my worst case bit error would be 3 minus 0.23. So if I wanted to do that, I calculate the log to the base 2 of 2 cubed over 3 minus 0.22, 3 minus 2.77 is 0.23. I can't take the log of a negative number, so I always have to do a magnitude. And we could calculate that here for this converter. And what does it come out to be? The effective number of bits is 5.12. Not really believable. As long as it's better than 3, nobody complains. 3 or better, nobody complains. The relative accuracy, instead of using VLSB, you still come up with 5.12 bits, and I don't understand why. Okay. I've never understood the difference between those two. I get the same numbers, and I am absolutely convinced that you always get the same numbers. But the pre-lecture quiz, somehow she got a different number, and I can't figure out where that came from. So anybody wants to complain about the pre-lecture quiz, send me an email, and I will lower the number of points on it. Somebody actually complained today. One person, I think everyone failed it except for one person. And the one person I helped. So 2 people. Okay, so data converters, we looked at all this stuff. And the reason why we use these, and you understand this, is what happened here? This looked okay this morning. Circuits. We got the analog world. We've got transducers and actuators. Most people who go to school understand the digital, in today's world, understand the digital world really well. They understand the computing, the signal processing, how to do digital algorithms for control. That was a really good model for a lot of years for engineering, electrical engineering education. Because what was going on is the old guys knew analog, and they were hiring new engineers to come in and do the digital parts that they didn't quite understand, and to do the programming that they didn't quite understand. And they could catch them when they made the stupid analog mistakes, because that's what they were good at. All those good analog engineers were mostly older than me. But I would listen to them, so I learned a lot from them. They've retired. The baby boomers are retiring. And so what's really going on in the real world is you got a lot of people who were like FPGA designers who have no handle on what's going on in analog. And there's a lot of people out there screaming for analog engineers now, but the universities have been teaching digital because that's what people's been hiring. So this is, again, and another advertisement for 490 in the fall, is I want to get you to understand enough analog that even as a digital engineer, you're not going to make these rookie mistakes I see professional people making. You're going to understand output resistance and why you can't hook a Arduino up to a motor and expect it to run. I've seen people in capstone projects do that. They were mechanical engineers. They hook an LED up to an Arduino, the light turns on, everything's fine. And then they say, but look, I hooked my motor up to the Arduino and it doesn't run. What's going on?
Telling me an LED is not the same as a motor?
Is it current draw capacity? Current draw capacity. So things like that, some really basic analog stuff, just so that you know how to use transducers and things like that. I'm not expecting to be able to duplicate an entire analog program, but get you to understand enough that you can actually build circuits that work. That is my goal. And there's a, and apparently that's I'm sorry, apparently that from what I've heard from other people, like VPs of engineering, that this is the best analog program they've got in Arizona right now. If you want to learn analog, there are some very good schools out there like Berkeley and a few places like that. I mean, there are people teaching it. The demand for analog engineers has gone up. Not as fast as digital engineers, but it has gone up. And a lot of people they end up learning it on the job, like Tyler Lee. He's an RF engineer now. He had no training in RF engineering, but he learned it on the job and then did what he could. So a lot of stuff out there. I just want to keep you from making rookie mistakes. This is Dr. Brower's final exam review. This is all she ever gave you. Feel sorry for you guys back then. This is just a review of what we've done this semester. We started out exam 1 stuff. We looked at digital CMOS, static CMOS circuits, pass transistor circuits, and dynamic circuits. 3 different styles. When we get to 490 in the spring, you'll see, like in the real world, just people jumble these and mix them all together to make a circuit that fits and meets the requirements. Usually not inside your processor itself, but in the drive electronics. In the you have the digital processor, and then it has to drive a memory array or drive some other circuitry. You need some kind of, there's usually op amps inside, even a memory chip. And then there's like special little digital circuits that need to fit in a 10 nanometer line like this, and they can only be, you want to make them as short as possible. So you mess around with these 3 different styles, the static CMOS, the pass transistor, and the dynamic logic, and it all kind of gets jumbled together into this weird amalgamation. So we'll look at, that's what we do in 490 in the spring, is we look at a lot of those circuits and go, okay, what does this do? This is an AND gate. This is a, it is just take these jumbled messes and figure out what they do. And we also look at the memory physics too. Then we looked at analog, and this was exam 2. We looked at a bunch of different stages, and remember the goal was to find input resistance, output resistance, and gain. Once we get there, we know the midband values, and we can successfully try to hook these up into multi-stage amplifiers. We also looked at current mirrors. Frequency response, we thought about, okay, where does the frequency start to roll off? Mostly looking for that FH, the point where the gain has dropped by half. That's called the 3 dB point. That's what I always call it. And it happens at 1/2 pi RC. If I give you a problem on the final exam and the only thing you're given is R and C, guess how you calculate the frequency? Everyone should know that, like off the top of their head. And then we looked at data converters. Yeah. So go back and do the practice final. There's a lot of problems on there. There's at least one problem on there that is amazingly similar to a final exam problem. If you don't just copy it, you should be able to get there. And where are we at? The final exam is Wednesday, April 28th, 3 to 5 p.m. You get 3 sheets of notes, and it's cumulative. So expect some problems on digital logic, expect some problems on basic MOSFET calculations, calculating ID with body effect and output resistance. Know when you have to add those in for yourself, and doing DC operating points of these transistor circuits and calculating the gain, the input resistance, and the output resistance. Yeah. Me and Dr. S had a long conversation about the input resistance, output resistance, and gain thing. And apparently he's got this book. It was published by IEEE. It's called 10 Essential Skills for Electrical Engineers. And that is one of them. And it was mostly done from an analog perspective. Some old guy wrote it. Didn't have anything in there on programming. Was it? What's going to happen to most of you? I hate to tell you this. You go out in the real world, probably 90% of you are going to become programmers. Mhm. You have to fight for that right.
That's basically how electrical engineering fields can look at. You got programmers and programmers who understand it.
Yes. And the programmers who understand analog are much more highly sought after than the ones who don't. You gotta know a little bit, especially when we're getting into these high speed circuits. So your clock speeds, if your clock speed's 10 gigahertz, I mean, when I was an RF engineer, I was designing a transmitter at 1 gigahertz. And I know people who are designing transmitters at 50 to 100 megahertz and looking at serious RF effects in there. If you think of your digital signals, if they're switching at 10 gigahertz, it is no longer just a straight wire across the board. You've got a transmission line, and you've got to kind of take some of that into account, or at least have some good sense of it. The people who are pushing the speed limits at Micron, the guy there has this brilliant 10 gigahertz oscilloscope. I mean, I was just, okay. But when he runs, when you're going up to like DDR6 and you're clocking faster and faster, what those digital outputs look like, even on that 10 gigahertz scope, is they look like sine waves, because you're not picking up those higher frequency components. And they're using analog signal processing techniques to get the data out faster. The data's coming out, they're reading the data so fast from the chip, they actually have to read it before it has time to settle. So they have like a phase lock loops and things like that on the output to say, okay, this is exactly a 16th of a clock cycle, and the clock's going at 10 gigahertz. And I'm going to predict whether this is, and I'm not going to wait for it to settle, I'm going to predict whether this was trying to write a 1 or a 0 based upon the slope of the line and the previous values of the signal. So I look at the 4 previous values of the signal, and I say, okay, so this is where the signal should be. If the slope's going up, it must be a 1. If the slope's going down, it's a 0. If I had a whole string of 1s and the slope is flat, well, then that's a 1. So I have to do predictive, and it's an analog circuit on the readout of this thing, and it's an RF circuit too. And just understanding programming and digital logic isn't enough to get you into this like high-speed world. And that was my favorite part of Micron, because it proved my point. Everything's analog. Digital's just a sloppy approximation.
I always wonder when Dr. Campbell came, he was talking about how like the future might be in like quantum
Yes.
sets, and I was just like, imagine having to like calculate like standard equation like stuff to figure out the state of the electron itself, because we're getting like so small.
Well, yeah, and it's actually, I mean, even when I was in school, when I started to grad school, well, before Ian was born, so I started probably, it was between when Gwen and Ian were born. I started probably in '89. They're only 2 years apart. So I started grad school, and even then, And they were talking, they were talking about, like 0.4 micrometers, 400 nanometer. And there was a small enough amount of current and a small enough number of electrons involved that quantum effects were really part of how the transistor worked. And mostly it's the physicists taking care of that, so you don't have to worry about it. But as you get smaller, the quantum effects start to dominate, and it gets to be less and less predictable what's going on. Yeah. And so, yeah, I took an entire year of quantum in I know what year it was, in 1989, 1990, because I was pregnant with Ian. I like practically gave birth during the final.
That's the story.
The final was his due date.
Oh,
And he was like this 10-pound baby, and I could barely fit in the chair. That's slightly irrational. But I took a whole year of quantum physics in the physics department, and I had people like test engineers. At the time, I was interviewing for a test engineering job. I interviewed for 3 different jobs at Motorola. These guys were laughing at me for taking quantum physics. And, yet the, people in SBS, it was already important and already, and I was glad I kind of got that edge and I could kind of look ahead because like, looking back, understanding the physics behind the devices has helped me because that's the stuff that stays the same. And what's going to change is the programming languages, the different EDA tools you're using, they change all the time and you have to learn those over and over again. But having that background and the stuff that doesn't change really helped me. Yeah. And you're not going to, when you start working, they're not going to expect you to know everything. In fact, Corey Klein,
yeah.
He's brilliant at everything, right?
Really.
And he had an internship at Micron, and they pretty much just told him, like, it'll be a year before you're productive. Because you're going to get another learning curve there, but it's going to be a learning curve or any place you go, it's going to be a learning curve in a more specialized area. So pick that area carefully. You might, a lot of people end up having choices. You have more than one job offer, so look at that, look at the industry, what you think the long-term projection is for that industry, because it's harder to change industries than it is to change jobs. If you're thinking about the job offer and you're saying, oh, this is a better job offer, but it's in a dying industry, it's a more interesting job. And then you look at, well, I've got this not so great job offer, but it's in an industry that's growing. You can always jump from job to job within that company or within that industry. Just build up your resume and put the things on your resume that you want to do. And there's a lot of jobs I did that I never wrote on my resume. Like I was always the designated person in the department to rewrite other people's papers. Because I could go through, it didn't matter what your native language was. I could read it and understand it and make a few corrections and make it flow. But I never write that on my resume because I don't want that to be my next job as being a tech writer. I write about the things I want to do next, and I kind of like build that up into the job I want. Yeah. Mm-hmm. And like, when I was at Motorola, we had a bulletin board out there, and it was full all the time of different internal job openings within the company. If you didn't like your job for whatever reason, and you had the skill set for that job, it was really easy to jump from group to group and get what you wanted. And that's what Tyler Lee's done at General Dynamics. As he started out there, they hired him in as a power supply designer or something like that, but he really wanted to do RF and he had no expertise. So they gave him like the worst RF job they possibly could. And he took that, did the RF for a while, and then he started getting better jobs through that. So there's a lot of opportunities out there. You just got to kind of like think about what's the thing you want next and prepare yourself for it. Get the skill sets for that, whatever it is. So I don't know. Let's see who's here. Jacob. Let's see. I'm just going to kill this because this can. Oh, there, I did the wrong thing. I wanted to do that because I want to see who all was here. Anybody come in that I didn't check off? No. Okay. So if you've seen the video or if I make a mistake on your attendance, you can always email me. No questions asked. I'll give you attendance points. Okay. I don't know. Anything else? This is the class that's kind of like, as far as industry in Arizona, it's the one strong thing I can get out of this program is for the microelectronics industry is really big in Arizona. You heard Dr. Campbell say that too. It's one of the big hubs in the world. It's Phoenix basically and Taiwan, and then there's a lot of manufacturing in Singapore and Southeast Asia and places like that. But this is really where they do a lot of the design work. It's in Phoenix, it's not in Silicon Valley. So this is where, and this is what kind of the things they expect you to know going in is yeah. And it's not as hard as it sounds based on this class. You get your little niche area and you figure it out. And even Nigel Gray, he graduated about a year ago. He's down at Medtronic, and I talk to him all the time, and he's just like, I can't believe, I really miss the intellectual challenge of school. Because what?
As an engineer, he's saying this.
As an engineer, he's saying this because you have these really, as an engineer, you have these really intense couples of weeks where you figuring everything out and you're figuring out the problem, and then you spend the rest of the time making sure that everybody else understands that problem and communicating with them, and then putting that together with something that's just working perfectly. And it's just it doesn't, yeah, it's not as hard as anybody thinks. Some of it's just stupid work. My bonus one semester, one quarter, was based on whether we could get one phone shipped out that quarter. And it's
one unit?
One unit. Well, this was the first unit. We had to get the first unit, and my bonus was like, a lot of times it was 50% of my paycheck. I mean, it could be huge. So the boss, he's pissed off everybody in the whole Chicagoland, Motorola, everything. They don't want to talk to him, and he's got to get this phone through shipping and receiving, and it's got to get out before midnight, right? And everybody leaves at 5, so it doesn't really matter anyways. So what does he do? Julie, and I spent an entire day doing nothing but walking around with a box and going, can you sign off on this so I can ship it? And they go, oh, and I'd smile and it'd be nice and everything, and nobody was pissed off at me, so it was great. And then the next question would be, who does it go to next? And they'd say, well, the next person who has to sign off it is that go over there. So I go stand in front of his office and go, can you sign this piece of paper?
That's what you had to do for that whole day.
That's what I did all day long. Yeah, for that one day. It was just basically, and I was like driving all over Chicago because some of the people weren't even in Arlington Heights. Some people were up in Libertyville, and you just drive around, stand in front of their office, and it's really way more effective if you stand in front of their office.
Well, yeah.
I got that phone out. It got recalled, but I got the phone out.
Oh,
Did not say it couldn't be recalled.
I know it just that was the standard we had to meet. We had to get one phone out. It went through shipping. So yeah, you do stupid things. You do things, and some people break phones, and that's their whole thing. And yeah, get along with people. Listen to the technicians. They know more than you think. Okay, so that's about it. I'm done. We'll do the review on Wednesday. Or no, we won't. We'll do it on Thursday. Yeah, this is a 280. Yes.
On February 11th, but that was the exam day. Because I took the exam.
Send me an email and I will go in and change it.
Oh, sorry.
It's that easy. Yeah, I just need to be sitting in front of my grade book to do it.
Okay.
Yeah.
You should be,